Hello everyone, good morning. Today we will be discussing about single source shortest paths problem or Dijkstra's algorithm. So what is a single source shortest path problem? It's basically given a specific vertex, we want to find the cost of the shortest path going from vertex, let's say vertex A, going to all of the other vertices. If we were to relate that in real life, we could think of it as given a specific location, I want to find the shortest, I want to have the shortest directions in terms of distance going from place A to place B, C, and D. So for example, if I am in USC Talamban and I wanted to go to Ayala, SM, and SMC side, doing a single source shortest path problem would allow me to find the shortest path going from, or not really the shortest path, but the cost of the shortest path going from Talamban to Ayala to Seaside to SM. So that's it basically. So given a directed graph G containing vertices and edges such that each arc has a non-negative label. So you'll notice that this is a directed graph. So I have arcs moving from a vertex to another vertex. Each of them have non-negative labels. This is important because in Dijkstra's algorithm, we make use of a function called min, which gets the smallest possible amount between two different paths. And a negative label would mean there's a negative path, and that would most likely become the shortest path, which is not something that we want. So it has to have a non-negative label. So the problem here is, or the single source shortest path problem is to find the cost. So take note, it's not finding the shortest path, but the cost of the shortest path. Meaning, for example, I want to find the cost of the shortest path from 0 to 1. I can check for any different paths from 0 to 1 and calculate the cost of the shortest path. So from 0 to 1, it's 10. Are there other paths going to 1? Let's try. 0 to 3 to 2, there's no way going to 1. 0 to 4, there's no way going to 1. So technically, the shortest path is from 0 to 1. And the cost of that path, which is what Dijkstra's algorithm solves, is 10. We'll try with a different vertex. Let's say I want to get the single source shortest path, the cost of the shortest path going from vertex 0 to 2. So we know that there is a path from 0 to 1, then to 2. There is no path from 0 to 2 directly. There's a path from 0 to 3 to 2. There is a path from 0 to 4, but there's no way to go to 2 from 4. So we have two paths to choose from. That's 0, 1, 2, 0, 3, and 2. The cost of the path is 10 plus 5 for 0, 1, 2. And the cost for 0, 3, and 2 will be 30 plus 20. So the cost for this specific path is 60. The cost for this specific path is 50. So we know that the shortest path, or the cost for the shortest path is 50. So we don't calculate, or we don't look for the shortest path. We look for the cost of the shortest path. So the problem allows us to find the cost of the shortest path from a given source vertex to all of the other vertices. So by the end of this algorithm, you will be able to calculate the cost of the shortest path going from 0 to 1, 0 to 2, 0 to 3, and 0 to 4. By mata-mata method, you can also do that one. We already got the shortest path from 0 to 1, which is 10. The cost for the shortest path from 0 to 2, we also calculated that to be 50. 0, 3, 2. The shortest path for 3, we can also calculate that using our eyes. 0 to 3, the path is just 30. That's one path. Let's try to look for a different path. 0 to 4, 100. There's no way to go to 3 from 4, so there's no path from there. 0 to 1, there is a path from 0 to 1, then 2. Is there a path from 2 to 3? No. So there's no other path for 3 from 0. So the shortest path is 30. The cost of the shortest path is 30. For 4, we have 0 to 4 is 100. Let's see if we can get to 4 from different paths. So from 0 to 3 to 4, the cost is 90. Let's try something else. 0 to 1 to 2 to 4. There is another path. That's 10 plus 50 plus 10. That's 70. So that's an even shorter path. The cost of that is even shorter. There is also from 0 to 3 to 2 to 4. That's 20, 10, and 30. That's 60. So that's the cost of the shortest path. It's 60. 0 to 3 to 2 to 4. It's very easy to do when you are doing the mata-mata method, but we will try to look into how that's done through code. And that's done by Dijkstra's algorithm. So the cost of the path may represent something different, like this could represent distance, but the cost might also be different, like something like time. So going from destination 0 to destination 2 might take 5 minutes, 10 minutes, so it could be different basically. So what is a form of application? I told you a while ago it could have been from the cost of the shortest path going from Talamban to different malls. A different application would be the graph is a map of airline flights such that each vertex represents a specific city, and each arc from a vertex to a different vertex is an airline route from one city V to a city W. So each of the arcs represent a route from V to W, and the label on that specific arc is the time to fly from city V to W. When we do the single source shortest path problem for this specific graph, we would be able to determine the minimum travel time from a given city to every other city on the map. So the solution to this problem is called Dijkstra's algorithm, and it's considered a greedy technique. Greedy because you're kind of trying out all the different paths. Ma'am Peña wouldn't call it greedy. She calls it exhaustive because we're basically trying to compare the different paths that are available. So we're trying to do the same thing that we did manually a while ago, but we're doing it with code. And how do we do that with code? We have this amazing pseudocode provided by the book. And shout out to Ma'am Peña, this is very easy to understand because she color-coded it. So there are different components when we are coding the Dijkstra's algorithm. The first component is highlighted in red. This is the set containing all of the vertices that we have already chosen, or we have already mapped out. So what does that mean? You'll see later, but you'll know that you need a set that contains vertices that you've already mapped out or visited or chosen. This blue one, this for loop, basically initializes an array D. What is array D? D represents the cost of the shortest path going from vertex V to vertex W. So it's an array containing the cost of each of the shortest paths. C is a labeled adjacency matrix. So C is your graph reference. And what this for loop does is it basically initializes my D. You will see that later. And then this for loop is the bulk of the algorithm. So in the algorithm, there are 3 steps. We choose a vertex W in VS such that DW is a minimum. We add W to S, or our set, and then for each vertex V in V minus S, or a difference between V and S, we do dv equals min dv wcwv. You don't need to understand that right now. Let's just go to the next slide and see what this means. So this is our simulation. So we started by initializing our set. And let's just say we are doing the shortest path problem for vertex 0. So that means our S contains 0. V is our universal set. If you remember what that means, it's just the set that contains all of the specific values. Or in this case, a set containing all of the vertices. So you see 0, 1, 2, 3, and 4 because in our graph there are 5 vertices from 0, 1, 2, 3, and 4. So S contains the vertex we are starting in, and take note, we don't always start at 0. We can start with any vertex. In this case, we are going to start at vertex 0. We now try to look at what happens in our initialization. So in our initialization, we are initializing D. You will notice that D, as I mentioned a while ago, is an array containing the cost of the path going from 0 to 1, 0 to 2, 0 to 3, and 0 to 1, 0 to 4. We can visualize that using the graph. The cost currently, the shortest cost currently from 0 to 1 is 10. There is no path from 0 to 2 currently because I can't find anything from 0 to 2. From 0 to 3, the shortest path is, or the cost of the shortest path is 30. And from 0 to 4, it's 100. That's in graph, or that's in our graph simulation. But if we were to look at it from the labeled adjacency matrix C, it's a lot clearer. And you'll notice that's what we are doing here. We are basically copying the row. The path from 0 to 0 is infinity. This is supposed to be 0 actually. I don't know why that's infinity, but anyways. Or, yeah. The path from 0 to 0, there is no path. The cost is 0. The cost from 0 to 1 is 10. 0 to 1 is 10. 0 to 2, there is no path. 0 to 3 is 30. 0 to 4 is 100. So we copied all of this together here. Gets? But because we are starting at I equals 1, we are not copying this specific value yet. So this will still be garbage. Essentially, we don't really mind if this is garbage, but make sure you just don't access this. At the end of everything, we need to set this to 0 because the cost of the path from a vertex to itself is 0. So let's try to simulate this. We've already simulated what happens for this for loop. We're basically copying this entire row and storing it here. If we were to start at a different vertex, let's say we started at vertex 2, the difference would be S would contain 2 and my D would contain this. Gets? You're not here, but gets, I hope. So let's try to start our simulation. Now for this simulation, I would have liked for you guys to be able to copy this or to view this, but I screenshotted it so that we can reference it every now and then. And you can find that here. But my face is blocking, so yeah, move that there. So let's move on to the simulation. So we are illustrating what D looks like. So D is basically our representation of the shortest path, but this is only a visualization. D doesn't actually map out or give you the path. It only gives you the cost or the shortest cost for the path. Okay? So take note this. Later on, you'll notice that it would map out to specific paths. But in reality, it's only storing the costs or the shortest cost. So don't get confused. So we'll start at x equal to 1, and we are starting here in our first for loop. So x is equal to 1, x is less than n. What is n? N is just the number of vertices. So in this case, n is 5 because I have 5 vertices. We'll choose a vertex w in v minus s. That's the first step. Do v minus s, that's a difference. So we're going to do the difference between v minus s. V minus s currently is 1, 2, 3, and 4. So we're going to choose a vertex from 1, 2, 3, and 4 such that D index W is a minimum. So we're looking for a vertex such that it is a minimum. So we're going to look at D 1, 2, 3, and 4, and we're going to look for the smallest value. D1 is 10. D2 is infinity, D3 is 30, D4 is 100. The smallest value there is 10. Therefore, I am going to choose vertex W, which is 1. DW is 10, so I'm going to use W to be 1. So that's why my W is 1. The next step is we add W to S. So you'll notice W is 1. So I added it into S. For each vertex V in V minus S, so we do V minus S again. So if we were to be coding this, it would be very cool if you guys made a function that allowed us to get the difference so that we would already be able to get the vertices. So the difference between V minus S is 2, 3, and 4. That means we have 3 V's to look into. V2, V3, and V4. So for each vertex V, V2, V3, V4, we will do D index V. So D index 2 gets the minimum. This is a function. The function will return the smaller value between 2 different inputs. That's basically it. Create a function min that given 2 specific integers or 2 specific inputs gets the smaller value. Min of dv. What is dv? D at index v, which is 2, this was infinity. So that's why it's infinity. D index V is infinity, and then we are going to check for DW and CW. DW just means starting from vertex 1 plus the path from W to V. Is there a path from vertex 1 to vertex 2? So let's look at our graph. Is there a path from vertex 1 to vertex 2? There is, and the cost is 50. So because the cost is 50, we did 10 plus 50, which is 60, right? And we are going to get the minimum between infinity and 60. The smaller value is 60, so D index 2 gets 60, which means infinity was replaced with 60. We do it again for index 3. Min of dv, which is dv. D index 3 is 30, so we start at 30. So what we're basically doing in this specific step is we're comparing the shortest cost currently with the possible shortest cost from this new path. So right now, the path from dv, which is 3, the cost of that is 30. That's from 0 to 3. We're trying to see if there is a path from 1, which is our w, from 1 to 3. So is there a path from 1 going to 3? There is no path from 1 going to 3. You can also check it from here. Is there a path from 1 going to 3? No, there is not. So that means CVW, or the edge, or the arc, is infinity. So that means we're comparing 30 and 1 plus infinity and getting the min, that's 30, and assigning it to dv. It's already 30, so there was no change that occurred. It's still 30, meaning there wasn't a path from 1 to 3. From 1 to 4, so let's try again. So dv gets min of dv. dv is 100, comma, is there a path from 1 going to 4? So let's check, is there a path from 1 to 4? No, there is no path directly from 1 to 4. Let's not use the term path, let's use the term arc. Is there an arc from 1 to 4? No, there is not. So that means it's basically 1 plus infinity, because there is no path from 1 to 4. There's no direct path, or there's no arc. So we get 100 and we set that here. Nothing changed. So I was able to do this operation for each of the vertices v. So we end this specific part of our for loop, and then we go back to this specific part. X plus plus, and then x becomes 2. Is 2 less than 5? Yes. So we continue. We'll now choose a vertex VW in V minus S. V minus S currently is 2, 3, and 4. So we are going to choose from D, D2, D3, and D4. We are going to choose the minimum. The minimum is 3. Because the minimum is 3, we do add W to S. So we add 3 to S. And then, let's go on to the next slide. So you'll notice W is 3. We added that into S. Next, for each vertex V in V minus S, so we're doing another difference. V minus S is 2 and 4. So we need to map out paths from 3 to 2 and 4. Okay? So we need V2 and V4. So we are just doing it all over again. Currently, D2 is, unsay value ni D2? D2 was 60. So, D2 or DV, which is 2, 60, comma, DW, what is DW? It's currently 30. So we're basically checking from W or from 3, is there a path going to 2? Is there a path going from 3 to 2? Or is there an arc going from 3 to 2? Yes, there is. And that path, or the cost of that specific arc or path, is 20. So we did 30 plus 20. This equates to 50. 50 and 60, we look for the min value. The answer is 50. So we overwrote the previous shortest cost, which was 60. We overwrote it with 50. And then we are going to check for the path from 3 to 4. So currently, the shortest cost is 100. D4 is currently 100. Now we are checking if the path from 3 to 4 is shorter than 100. So we're checking DW. DW is 30. And then we are checking, is there a path from W to V? Is there a path from 3 to 4? Let's look. From 3 to 4, there is an arc. That's 60. So, we just did 60 here. That's what is the C. So, we compare 90 and 100. What is smaller? It's 90. So, I overwrote my D. D4 gets 90. And you will notice it's also mapped out in the simulation. So the path from 3 to 2 is 20 and the total cost is 50. So if I wanted to go from 0 to 2, I can go from 0 to 1 to 2, which costs 60, which is 50 plus 10. And I can go from 0 to 3 to 2, which would only cost me 50. So that means the shortest cost is 50, from 0 to 2. Same with 4. Originally, my shortest path was 0 to 4, 100. But then I realized there is a path from 0 to 3 to 4, and it only cost me 90. So that means the cost of the shortest path is now 90. So we ended our for loop here, and then we are going to go back here. X plus plus, x becomes 3. 3 less than 5 is true. So we are now going to choose another vertex W in V minus S. V minus S is 0, 1, 3, 0, 1, 3. So I'm remaining with 2 and 4. So that means I need to choose a vertex between 2 and 4 such that it is smaller. DW is a minimum. In that case, my W should be 2 because 50 is smaller than 90. So we add W to S, so I'm going to add 2 here, and then I'm going to do this all over again. So you'll notice I added 2, my W is 2. For each vertex in V minus S, the only remaining vertex is 4. So I'm basically mapping, is there an arc from 2 to 4? And let's see the path if it's, or the cost of the path if it's cheaper. So from D4, the last minimum path was 90. So min 90. And then the current minimum path is calculated by checking. The path from 2 is 50. And we're going to check, is there a path going from 2 to 4, or is there an arc going from 2 to 4? Let's take a look at the picture. Is there an arc going from 2 to 4? Yes, there is. And the cost is 10. So we do 50 plus 10, which is 60. 60 and 90, what is smaller? It's 60. So we're going to update this to be the newest, shortest cost. So from our example here, we will notice that going to 4, there are multiple paths. There's 0 to 4, which cost 100. 0 to 4 from 3, which cost 90. And 0 to 4 from 0 to 3 to 2, then 4, which only cost 60. But you'll notice that this specific simulation doesn't actually, it only visualizes the shortest cost, but my result, which is D, an array containing the shortest cost or the smallest cost, doesn't actually tell me the path. It only tells me the shortest cost. So given a D, I will know that there is the shortest cost going from point A, which is 0, to vertex 4 or vertex 2 will be 50 or 60. So that's the end of our simulation for Djisktra. Because after this, what will happen next? I am going to do x plus plus again. X becomes 4, and I need to check for 4. So I'm not actually done there. Okay, 4 less than n, 4 less than 5. So x becomes 4, and dw, we're going to choose a dw in v minus s. V minus s is 4, so that means the only last choice is 4. So I chose the vertex 4 and I added 4 to S. For each vertex in V minus S, so take note, V minus S. V minus S no longer has any vertices because they are the same. So meaning I didn't have any vertex to check. I don't have any more things to map out. So I didn't do anything in this for loop because there's no vertex to check anymore. So I'm gonna do x plus plus. X becomes 5. 5 less than 5 is false. So I was able to get my shortest cost. by the end of all this, please do not forget to set this to 0, because the cost from 0 to 0 or 0 to itself is 0. So what do we get from all of this? At the end of this, you will have an array containing the cost. You will not have the path, but you will know that there is a path that costs only 50, a path that only costs 60. So the shortest path from 0 to 1 is 0 to 1, which is 10. The cost of the shortest path from 0 to 2 is 50. 0 to 2 from here is 60, so this is not the shortest path. 0 to 2 from here is 50. So this is my shortest cost. 0 to 3 is 30. That's here. 0 to 4. There are 3 ways I can go to 4. That's 0 to 4, 100. So that's not it. 0 to 4 is 90. That's not it. 0 to 3 to 2 to 4, that's 60. And that's my cost of the shortest path. So the Djisktra algorithm will give me the cost of the shortest path going from a specific vertex to all of the other vertices. At the end of this lecture, I would say any questions, but then we can't do that. So if you have any questions, you're free to post them on the chat. Our chat. You're free to post them on our chat. Just take note, I think you guys will be able to do this very easily. My tips would be, I would suggest you have a function that would calculate the difference, so that when you go here, you can calculate the difference v minus s. And when you go here, you can also calculate the difference v minus s. Everything else, you can also write a min function if you want, but then do you really need a min function when you can just do this? If this is greater than this, then use this, otherwise use this. But if you want, you can really make a min function. Everything else, I think you can do it already. Congratulations, guys. This is the end of my lecture on Djisktra. I hope you were able to understand. Bye.